Welcome back. In this section, we'll be talking about equations and graphs of ellipses, which is the mathematical name we give for a shape you would probably call an oval. So, if we're talking about an ellipse, the formal definition that we have for an ellipse is that there are 2 points, two focal points, F1 and F2, and that every point on my ellipse has the property that the distance from that point on the ellipse to the first focal point plus the distance to that second focal point is some constant. And that would be true for any point on that ellipse. So any other point on the ellipse, its distance from the first focal point plus its distance to the second focal point should also be the same constant. One thing that you'll notice here is that the two focal points that I've drawn happen to be along the longer side of the ellipse. For an ellipse, we have a longer side and we have a shorter side. So here, the horizontal direction is the longer one for this one that I've drawn, and the vertical direction is the shorter one for this ellipse that I've drawn. That longer side, we call this the major axis. This would be the major axis of our ellipse, and that would be the side that contains those two focal points. For the shorter side, in this case the vertical side, we would call this the minor axis of the ellipse. Now, one thing that's similar to our definition for an ellipse and how we're going to graph it, similar to how we did things with circles, is that when we looked at a circle, we started with finding its center, then finding the points above, below, to the right, and to the left of that center point. And that was how we plotted our equation for a circle. We'll do a similar sort of thing with an ellipse. So with an ellipse, along the major axis, you have the two endpoints, which we call the two vertices of the ellipse. And in the shorter direction, along the minor axis, the endpoints of those we call the covertices. So we have two vertices, we have two covertices, and then, as before, right in the middle, we have the center of our ellipse. So taking a little bit of a look at this diagram here, you can see that there's two basic shapes that we're going to be able to see. One would be the shape where the longer side, the major axis, happens to be parallel to the x-axis. And we have one where the longer side, the major axis, is parallel to the y-axis. So we won't be dealing with anything where it's an ellipse that's tilted on its side like this. So we'll only be having ellipses that we'll look at where the major and minor axis are parallel to the x and the y-axis in some order. Also, for the graphing purposes for us, we're not really interested in the focal points, the two foci. They don't really help us with the graphing side of things. We only need to know where the center is and where the vertices and covertices are. So that's why you can see I don't have the two focal points drawn here on my diagram. So when we're thinking about the equation of an ellipse, the questions we're going to want to know would be, how can we tell where the center is? How can we tell where the vertices are? How can we tell where the covertices are? And also how to distinguish between these two possibilities. How can we tell whether the major axis is parallel to the x-axis or the y-axis? So for the equation of an ellipse, you'll see that it's in a sense similar to the equation that we had for a circle. Remember that for the equation of a circle, if you had the center hk and a radius r, that the equation was x minus h squared plus y minus k squared is equal to the radius squared. And we have something kind of similar going on here. You'll notice that in the equations that I have for the standard form of an ellipse, there is an x minus h squared and a y minus k squared, just as we had for equations of circles. So that part is similar. There's one twist here, which is that, of course, Unlike a circle where there's a constant radius in all directions, for an ellipse, depending on where the major axis and where the minor axis is, one side of the ellipse or one direction will be longer than the other. So for that part, we have two constants that we have, a and b, two positive real numbers. And here I'm assuming that a is going to be the larger of the two numbers. So if we're interested in figuring out, is that major axis parallel to the x-axis or the y-axis, it really depends on where is that larger of the two numbers. If that larger of the two numbers, if a is squared and below the term that has the x in it, then the major axis is parallel to the x-axis. And if it happens to be in the denominator for the term that has the y, then it must be parallel to the y-axis. So by comparing the denominators for these two fractions, whichever denominator is the one that's larger, that would be the direction that's the major axis direction. So if the larger value is under the x's, well, then that must be that the major axis is parallel to the x-axis. And if it's underneath the y's, then the larger axis, the major axis, is parallel to the y-axis. The other part here is that when we start graphing from our center, that A and B are the units on either side of the center that will find our vertices and our covertices. So, for example, if your major axis was parallel to the x-axis, then from your center, HK, you would go A units to the right and A units to the left, and that would be where your two vertices would be found. And that from the center, you would go B units up and B units down, and that would be where your covertices would be found. And then you'd be able to connect the dots and draw your ellipse. So one thing to note here, of course, is that if you are going A units to the right and A units to the left, then for the major axis, the total length of it from left to right should be A plus A, or 2A. So the major axis has length of 2A, and similarly for the minor axis, if you're going B units up and B units down from the center, then that's a total distance of 2B. So the minor axis has a length of 2B. Okay, let's put this into practice. I've got an equation of an ellipse in standard form. I'm just going to rewrite it to make it a little bit more obvious for myself here. So x plus 3 squared, I'll rewrite that as x minus negative 3 squared. And instead of 9, I'll write that as 3 squared. The second term, y minus 1 squared over 25, I'll rewrite that as y minus 1 squared over 5 squared. Okay, so the reason I've done this is to make a couple of things easier to see. Number one, the center, I can now see, has coordinates of negative 3, 1. There's the coordinates for the center of my ellipse. Now the next part, where is the major axis, where is the minor axis? Remember that we just have to ask ourselves, of the two denominators, which one is the larger one? And that would be the 5 squared. And we can see that that's in the term with the y's. So that means that the major axis must be parallel to the y-axis. And that means the minor axis is parallel to the x-axis. So we'd have something with a large vertical direction and a smaller horizontal direction. We'd have an ellipse with that kind of a shape. All right, so next part is determining what are the lengths of our major and our minor axes. And this is where we need to remind ourselves that if we're thinking about the major axis, the 5 that I have there for 5 squared is telling me that I'd be going from the center 5 units above and 5 units below. So that means that my major axis should have a total distance of 10 units. And then similarly, For the minor axis, we're traveling 3 units to the right and 3 units to the left. So that means the minor axis has a total length of 6 units. So now that we've got that settled, it's easy enough for us to find the coordinates for our vertices and our co-vertices. So again, we have our center of -3, 1, and we said that we were going to go for the two vertices 5 units up and 5 units down. So if you went from that point 5 units up, you'd be adding 5 to the y coordinate. That would make you have the point -3, 6. And if you went 5 units down, you'd be subtracting 5 from the y coordinate. You'd be at -3, -4. And now for the minor axis, we said that from the center we're going 3 units in either direction, 3 units to the right and 3 units to the left, which means we're going to be adding or subtracting 3 from the x coordinate. If you went 3 units to the right, you'd be adding 3. That would give you the point 0, 1. If you went 3 units to the left, you'd be subtracting 3 from the x coordinate. That would give you -6, 1. And so now we've got just about everything that we need. I have my center, I have my 2 vertices, I have my 2 co-vertices, and so the only thing that I really need to do now is just plot them and graph. So you can see here that I've already done part of the work for me, which is getting my axes drawn, having my x-axis labeled, my y-axis labeled. I have tick marks that I've labeled along my x-axis and along my y-axis. So I have my axes all ready to go. I just need to now start plotting my points. So I'll start with the point -3, 1, my center. And while I'm here, I'll label it. And now I'm going to plot my 2 vertices. I had -3, 6 and -3, -4. So from the center, going 5 units above and 5 units below. And then also from the center, going 3 units to the right to 0, 1, or 3 units to the left, -6, 1. All right. So now the next thing for us to do is to draw our ellipse. So trying our best to make a nice smooth shape. Going from my vertices to my co-vertices and around again. That's reasonably good. There we go. And so the last thing that I would want to do is, of course, to finish by labeling my equation. So I'm just going to label x plus 3 squared over 9 plus y minus 1 squared over 25 is equal to 1. Remember that for a well-labeled graph, you're going to want to make sure that you have plotted your points, you have labeled your points, you've labeled the equation, you've labeled your axes, you've labeled your tick marks. You'll notice that the only point that I didn't label was this point, 0, 1, and that's because it's on the y-axis at a tick mark, so I don't really need to write in the coordinates. If you do, that's fine, but you don't have to. So this I would consider a nice, well-labeled graph of my ellipse. Okay, one more problem before we have a pause. In this problem, we have an ellipse where we know what the center is, we know where a vertex is, and we know one point on the ellipse. And what we'd like to do is come up with the equation of this ellipse in standard form. So the first thing just to think about with this is this an ellipse where the major axis is parallel to the x-axis, or is it an ellipse where the major axis is parallel to the y-axis? That's our first thing that we'll need to decide for ourselves. And so I'm just going to do a little bit of a doodle here on the side. This is not a proper graph by any means. I'm just plotting down roughly the center point negative 3, 4, and the vertex that I have 5, 4. The reason that I'm plotting them is just so I can get in my mind, is the vertex to the right or left of the center, or is it above or below the center? In this case, I have my vertex is to the right of the center, and in fact it's 8 units to the right of the center. That means that the other vertex would be 8 units to the left of the center. In other words, you could figure out, if you wanted to, that the other vertex would be negative 11 quarters. Now, the nice thing here is that we can see that, number one, the major axis is parallel to the x-axis, and number two, it's plus or minus 8 units from the center to the left or to the right to get to the two vertices. So that means that when we're thinking about the equation of our ellipse, number one, we have the center, negative 3, 4, so we'll have an x minus negative 3 squared. There'll be a y minus 4 squared. And that for the two terms, the one involving x and involving y, the larger denominator will be under the term involving the x's, and that's because we had determined that there was going to be the major axis parallel to the x-axis. And we also figured out that from the center to the vertex it was 8 units, which means that the denominator here should be 8 squared. So if we're thinking back to the form of the ellipse equations that I gave a few slides back, here we're in the first scenario where we have the major axis parallel to the x-axis, and we've determined that A is 8. So the thing left for us to figure out is, what is B? What is B for this, or what is our distance from the center to the co-vertices? So just to clean this up a little bit, I have in the numerator x plus 3 squared, and in the denominator 64. And now I'm going to use that last thing that I haven't touched on yet, which is that we have one other point that we happen to know that's on the ellipse. We happen to know 1 comma 4 plus root 3 is on our ellipse, which means that this point must satisfy this equation. If I put in that point for x and y, left side and right side should be equal to each other. So I could put in 1 for x, and I could put in 4 plus root 3 for y, and left side and right side would be equal to each other. This makes things a little bit easier for me because now you notice there's only one unknown in this equation. There's only b, so now I'll be able to solve for b. This little first fraction that I have here, the numerator, 1 plus 3 is 4. 4 squared is 16. So that first fraction is 16 over 64, which simplifies out to really just give me 1/4. For the second fraction, the numerator, the 4 and the minus 4 would cancel, so you'd really just have root of 3 squared, which is just 3. So everything really simplifies down to just 1/4 plus 3 over b squared is equal to 1. And so now what I'll do is I'll bring that quarter to the other side. So I have 3 over b squared is equal to 3/4. And then multiplying both sides by 4/3 or dividing both sides by 3/4, however you want to imagine that, we find that b squared is 4. And then from that, we can say, well, b must be 2. Now, you might just want to put a pause here and say, why am I not saying plus or minus 2? Why am I just saying that b is 2? And this is to remind ourselves what b is measuring for us. B is a distance. B is how many units to the right or to the left, or sorry, in this case, how many units above or below, rather, our center will we find our co-vertices. Also, the reason why I have not a plus or minus here, why b is just 2, comes back from the original definition that we gave for the equation of an ellipse. We said that a and b, the two values we were finding, were positive real numbers. That's the other reason, the bigger reason why I didn't say that b was plus or minus the square root of 4, why I said b was just the positive, why b was just equal to 2. So now we have everything we need, and now we can write our equation of our ellipse in standard form. So we now know that b is equal to 2, or b squared is equal to 4. So we can take this equation that we'd had and rewrite it with b squared replaced with 4. We'll have x plus 3 squared over 64 plus y minus 4 squared over 4 is equal to 1. And there we go. That would be the equation of our ellipse in standard form. And if we wanted to, again, we know that from that center of negative 3, 4, that we'd be going 8 units in either direction, left and right, and that we'd be going 2 units in either direction, above and below, if we wanted to graph it.